So we're in chapter 13, and we're looking at page 400 is where we're starting. And we've got some power supply, some capacitor, and a resistor. And the capacitor has some capacitive reactance X of C. The resistor has some R associated with it. The power in the capacitor is going to be I squared X of C. The power for the resistor is going to be I squared R. And the, did I leave anything out? And we have apparent power. So power apparent, which is what the meter is going to read going to your house, is going to be the square root of power across the resistor squared plus, although that doesn't look like a plus sign, plus the power of the reactance squared. And the phase angle of the power is going to be the arctangent of minus X of C divided by R. Because X of C, if I was thinking of it as a direction, is in the minus I direction, and that's why I'm putting a minus sign there for. And your calculator will give you tangent in the first and fourth quadrant, so this would be a fourth quadrant answer sitting down that way. Theta would be sitting there, and that would be a negative angle. All right, so all those things are okay. You also have a... You can also find it as the angle is going to be the arctangent of minus the power reactance divided by the power resistance, because that's going to be the same ratio. I squared times those. So I'm just getting rid of the I squared guys and replacing them with those guys. So that's the same equation, just written a little bit differently. Now, a circuit has a power factor, and we'd like that power factor to be as close to 0 as possible to save money, is the issue. So apparent power is what I'm being paid, is what I'm paying for. I'd rather pay for reactant power, which is the real part only. And in order to do that, I want the power factor to come down to something else. So the power factor is going to be the power real divided by power apparent. It's also going to be the cosine of theta is also the power real divided by the power apparent. And that's going to be the same as the power factor. So sometimes we say power factor and we just cosine of the angle, or we have the power factor, we have to find the angle, or we know real power or apparent power, we can find the power factor. Either way, those are all things that we can do. All right, now, if I have a circuit that's in parallel, so I've got resistors in parallel, then resistance total is going to be 1 over R1 plus 1 over R2, right? If I have capacitors in parallel, we know that the capacitance is going to add, but if I know XC1 and XC2, then XC total is going to act just like resistance does, 1 over XC1 plus 1 over XC2. And if all we use is magnitudes in our calculations, we're going to be okay. This is going to be a minus 90 phase shift. And now if I go and I put a capacitor in parallel with a resistor, then my impedance total is going to be 1 over the square root of 1 over X of C squared plus 1 over resistance squared. So I end up because my resistor and my capacitor are 90 degrees out phase with each other when it comes to current and voltages, that's going to cause me to do a different type of calculation for impedance when I have both of them in there. All right. If I consider an XL, a circuit with a capacitor and an inductor in it and a resistor in it, and I ask myself, what is the current through the capacitor, what's the current through the resistor, and how does that relate to current total? Well, current total will be the square root of the current through the capacitor squared plus the current through the resistor squared, for the same reason as, because these guys are still 90 degrees out of phase. And I have a phase shift in the circuit. The phase shift is going to be the arctangent of the Y component guy, IC, divided by IR. So I can calculate a phase angle. If I'm looking at impedance, I'm looking at the impedance of the circuit. Well, if I know the source voltage, I got some voltage source coming in, and I divide it by the current total, whatever that might be, then that's going to give me the impedance. Total. That's going to, yeah, current total. That's going to be the same answer as this answer would be, doing it differently. But those two answers are going to be the same answers.
That gives you impedance total, right?
Well, impedance is impedance. I wouldn't normally put a T there, but the book has a T there, so I'll put a T there. Okay, turning the page. Another word, subceptance and admittance, are two words we don't use very often, but we have conductance G is 1 over R, and then we have B of C, which is my acceptance, is going to be 1 over XC. And is it AC? AL, I think. I don't know what it is. 1 over XL. The admittance has to do with inductance. The subceptance have to do with inductance. The admittance has to do with capacitance. Neither of those things have I ever used in polite talk any place other than this particular time every year. So those things won't be on the final exam. But they do combine into a capital Y guy that probably has his own name. And it's G squared plus BC squared for a circuit that's RC. And what is that called? I don't know. That's admittance. All right, another word that I don't use. All right, turn the page again. And now the issue is, I don't care about any of that stuff. That's all repeated. That's all repeated. Nothing new there. I guess we're going to do problems next. Now, someplace in the last two chapters, we missed the charging and the discharging of a capacitor. And I don't know why. So we'll look at that. But if I have a capacitor and a resistor, no, this isn't a problem. And I throw in a switch, and this time I'm going to use a battery here. So I have some voltage source, which is a battery. The voltage across the capacitor is 0 at t equal to 0. So I don't have any across there at all. I drop the switch. Current is going to be limited by the resistor, but I'm going to start building up positive charge on my capacitor, and negative charge is going to be showing up on the other side of the capacitor, and I'm going to charge on a path that looks like that, and I'm going to be 63% complete on my charge in one time constant, and my time constant is going to be RC. So whatever the resistance is times the capacitance, that's my time constant. In one time constant, I'm going to be 63% charged. After 5 time constants, I'm going to be fully charged. Now, in reality, in a mathematical point of view, you're never going to be fully charged. Okay, but we're technology people, so in 5 constants, we're going to make it there. And we will use that later on. Okay, back to homework problems. Which one would we quit on?
6 was the last one.
6? So we're doing 19. Number 19. Okay, so I want the impedance. I want the current, probably total. I want the voltage and power values. Okay, so I want current total. I want current for the capacitor, current for the resistor, which ought to be the same number, right? And I want power for the resistor, power for the capacitor, and I want voltage. Voltage across the capacitor, voltage across the resistor. Okay, so those are the things that I'm looking for. And now I'll go and draw a circuit, and I'm using A. So I've got 10 volts. That's an RMS value. All my answers are going to be in RMS. I'm not going to write it down. It just is. 500 hertz. Sounds like something that would be used on an alien spacecraft. Resistor. Okay, so I got 12K, 51 nanofarads. Nano is 10 to the minus 9th. So the first thing I need X sub C. X sub C is 1 over 2 pi 500 times 51 nanofarads. And 2 times pi times 500 times 51 double E 9 minus equals 1 over 6.2K. 6.2K. Alright, so the next thing we want to know is impedance. Impedance is going to be the square root of 6.2K squared plus 12K squared. We can put that in our calculator without the K, and then we can add the K at the end. Squared plus 12K equals square root 13.5K. 13.5K ohms. We can write that up here. 13.5K ohms. We want to know the total current. Current total. Voltage divided by impedance. The voltage is 10 volts divided by 31.5K. $13.5K. 740 micro. 740 microamps. 740 microamps. 740 microamps. 740 microamps. The voltage across the capacitor. Okay, so voltage across the capacitor is going to be current across the capacitor times X of C. 740 microamps times 6.2K. .6 volts. Voltage across the capacitor, 4.6 volts. Voltage across the resistor, 740 microamps times 12K. 8.9 volts. I'm going to do an idiot check. 8.9 squared plus 4.6 squared equals square root 10 volts. So I did an idiot check to see that if I take is 10 volts question mark equal to the square root of 4.6 squared plus 8.9 squared, and yes, it is. Check. 8.9 volts. The power through the resistor will be voltage times current. What's the current? 740 microamps times 4.6 volts. The voltage across the inductor, the power of the inductor, voltage resistor, voltage capacitor, 740 microamps, 8.9 volts. Uh, 3.4 milliwatts. Six point six milliwatts. And I think I'm done with 19. Am I done with 19?
Yep.
All right, moving on to 27. All right, I guess I have to write those numbers up here. 3.4 milliwatts, 6.6 milliwatts. All right, done with 19. Number 27. Calculate the impedance currents power for the A circuit. All right. I need the impedance. I need the current through the resistor, the current through the capacitor, and I need the power through the resistor and the power of the capacitor. Okay, so those are the things that I'm looking for. As I get them, I'll put them there. I have a circuit that is 2 volts, 18 kilohertz. That's a pretty weird frequency. And then I've got a guy here that's sitting at 10 nanofarads, and somebody over here at 1.5 kilo ohms. Okay, first thing we're going to find is X of C. X of C is 1 over 2 pi F times 10 nanofarads. Notice that I am not doing much calculating in my head today. That's not because Raimundo gave me a headache. It has nothing to do with that at all. Has everything to do with you can't do it in your head with these numbers. 880, we'll call it. 880 ohms. Okay, first thing we'll do is calculate impedance. Impedance, 1 over the square root of 1 over, what is the resistor? 1.5K plus 1 over 880 squared. Okay, so that's the number we're doing. Okay, 1.5 W3 1 over squared plus 880 1 over squared equals square root 1 over 759. 759 ohms. We'd expect it to be smaller than the smallest guy, and he is. And I know we'll put a T there for total, but impedance normally means total. 759 ohms. All right, now I'm looking at the current through the resistor. That has to equal the voltage. What's the voltage? 2 volts. 2 volts divided by the resistance, 1.5 k ohms. Um, 1.3 milliamps. 1.3 milliamps. The current through the capacitor has to be 2 volts divided by 880 ohms. .3 milliamps. Okay, so 1.3 milliamps, 2.3 milliamps. Power through the resistor. Power through the resistor, I squared R. Anybody remember what current was? Oh, right there. It's right there in plain sight. 1.3 milliamps. If I didn't have my trifocals on, I'm sure I could see it. 1.5 K. And the power of the capacitor, I squared X of C. 2.3 milliamps squared, 880 ohms. So those are the numbers we're looking for. 1.3 E3 minus squared times 1.5 E3, boom, 2.5 milliwatts. 2.3 E3 minus squared times 880, 4.7 milliwatts. Okay, so 2.5 milliwatts, 4.7 milliwatts. All right, 2733. 33. Calculate the component voltage and current values as shown in A. Okay. So I guess we'll write those down. So all we want to know is voltage R1, voltage R2, voltage capacitor, current R1, current R2, current through the capacitor. Okay, that's all we care about. Okay. Excellent. Moving down, drawing a picture. Got one resistor, 150 ohm. I've got a capacitor and another resistor, 1 microfarad, 1K, and I'm at 18 volts, and I'm at 250 hertz. Okay, so the first thing we're going to look at is X of C, 1 over 2 pi 250 times 1 microfarad. we'll call it 640. 640 ohms is what we'll call it. Yeah. Want me to throw in a hertz there? Is that what you're complaining about? 50 hertz. That better? All right, now I know that. So now I'm going to find the impedance across the parallel path. 1 over the square root of 1 over 1,000 squared plus 1 over 640 squared equals. Okay, so 1,000, 1 over squared plus 640, 1 over squared equals square root 1 over 540. 540 ohms. Current total. No, impedance total. Impedance total equals R1 plus Z across the parallel path. Okay, so now we need to know the phase angle of those guys. So the phase angle of the parallel path is the arctangent of minus 640 over 1,000. Minus 640 over 1,000. Okay, so 640 divided by 1,000. I guess I didn't have to do that. Arctangent. So our phase angle is 32.6 degrees. Angle minus 32.6 degrees. Okay, now, so I got 150 ohms plus the real component of this, which is the cosine. Okay, so 540 times 32.6 with a negative sign. Cosine equals, okay, so I've got 454.9 plus the other guy. Is it 540? Yeah, okay, so 540 times the sine, 32.6 with a minus sign, sine equals minus 291i. Alright, so my total current is going to be, oh, this isn't total current, this is total impedance. Who's going to tell me that anyway? Somebody must have been thinking about it. Total impedance, 605 minus 291i. And now I'm going to do a polar to rectangular conversion. 605 xy key 291 with a minus sign equals third function changed to polar. And we end up with 671. And we'll throw in an angle, but I don't think we're going to need it. At an angle of minus 26 degrees resistance. Okay, so that's my impedance total. Now, I wasn't asked for impedance total, right? But now I can find current total. So current total equals the voltage. What's the voltage? 18 volts divided by impedance total 67.1 angle minus 26 degrees. 18 divided by 671 equals, so what we'll call it 27 milliamps at an angle of 26 degrees. That is going to be the current through resistor 1. 27 milliamps. Angle 26 degrees. Okay, now we're going to find the voltage across resistor 1. So the voltage across resistor 1 is going to be what? Current through resistor 1, resistor 1. Okay, so 27 milliamps, angle 26 degrees, times 150, times 150. Four volts. So I got 4 volts, angle 26 is going to be my resistor 1 voltage. 4 volts, angle 26. Okay, now I'm going to find the voltage across the parallel path. Okay, so that's going to be 18 volts minus 4 angle 26. Okay, so that's going to be 18 volts minus, and then I'm going to change 4 angle 26 to a rectangular form. 4 xy key 26 equals second function change to rectangular form 3.6 plus 1.8 I. Alright, so now I'm going to have 18 minus 3.6, boom, 14.4 volts, minus 1.8 I. I'm going to now change that back to a polar form. I'm going to go 14.4 squared plus 1.8 squared equals square root. I'm going to do that this time. 14.5 volts. And do I care about the angle? I'm just going to skip the angle. All right, so I'm going to have 14.5 volts across both this resistor and that capacitor because they're in parallel. Okay, so the current through resistor 2, 14.5 volts divided by resistor 2, 1K. 14.5 milliamps. The current through capacitor, 14.5 volts divided by, is it 880? 880 ohms. $16.5K. No, 16.5 milliamps. Okay. 14.5 milliamps, 16.5 milliamps, and I am all done. Okay, last problem, number 39. Determine the potentiometer setting that will provide an RMS value of 20 milliamps in the circuit. Alright, so I guess that's what we have to do, number 39. Alright, so I got something here, and I got 10 volts, and I got 100 hertz. I got a capacitor, and I got a variable resistor, and this is 4.7 microfarads, which implies that X of C is equal to...
Is that a resistor?
Which one? The guy in the bottom? It sure is. I can tell in my book. You got your book open? 2 times, you want me to make a better one?
Yes, please.
Times 100, too bad, times 4.7 EE6 minus equals 1 over. So I have 340 ohms. 340 ohms. And the front row wants me to draw a better variable resistor. Huh? Oh, 300, yeah. You're right. Yes, definitely. 300. What does your calculator say?
What was the,
Is
what
that
was the
better?
equation?
What equation? XC? XC is equal to 1 over 2 pi 100 hertz 4.7 microfarad. It hasn't changed. We've used it over and over again. Okay, so that's the case. All right, now current. Well, impedance. Impedance is going to be the square root of 340 squared plus r squared. Okay, so we know that. And we know that current total is 20 milliamps. 20 milliamps. 20 milliamps, which has to equal voltage 10 volts divided by impedance. All right, so I got 0.02 is equal to 10 divided by the square root of r squared plus 340 squared. Okay, so I'll rewrite that 0.02 square root of r squared plus 340 squared is equal to 10. And I'm then going to square both sides of the equation. Well, before I square both sides of the equation, I'm going to divide this guy by 0.02. Right? So I'm going to have r squared plus 340 squared is equal to 10 divided by 0.02 gives me 500 squared. Okay, so r squared becomes 500 squared minus 340 squared. R becomes the square root of 500 squared minus 340 squared. Notice that it could be plus or minus, right? But we're not going to have any minus resistances yet, not until chapter 22 or 23. So 500 squared minus 340 squared equals square root. So the resistance is going to be 366 ohms. Okay, done with that. Done with chapter 13. I get to pass out the study guide and study.
No, nothing, bro. It's just what it is. I'm not using any notebook, I'm using book.
Huh? Oh, you didn't hear me? I said that if you already printed out the study guide, because it's been sitting on the website for the last 4 days, you don't have to get one. Okay? That's what I said.
Yeah.
So you're supposed to put a new file inside that you just put on there this morning.
Tú tienes verde vuelta, cabrón, ¿eh?
Una chingada ahí, güey. No, you gotta say no mames, güey.
¿Ah?
No mames, güey.
No mames, güey.
Yeah.
Insult.
Yeah, no, it's like, literally, yeah. Like, when you don't cut the own.
Whatever, Sharon.
What is that different than that?
What's with you, Wesley? No.
Well, that was silly. I left my camera going over here while I was passing the thing around. Okay, so I got to find the study guide.
Study guide. Study.
I'm not on the website.
Just say continue.
I'm blocked.
No, just go to the red little deals. Just
The
continue.
red thing?
No, bottom.
What thing?
Little small.
This one here?
Go back to that.
Yeah, right here it's saying that I'm not on the internet. Oh, this one here?
Yeah.
Close this page.
No, go that way. That one.
Continue anyway.
You got it.
Oh well.
We set the terms. I set the terms.
I may have typed in the wrong thing too.
Bang.
Okay. Well, oh, I don't want to be here.
Queer guy that got paid to do that.
Well, it's currently 1:43, Raimundo. If you're going to make your appointment, you better leave now.
Yeah, but I cannot leave without getting this.
Yes, you can. It'll be on the website.
Yeah, but it's not the same.
Yeah, it is.
He's pregnant.
Those are my exact thoughts.
Gonna have some coffee meetings?
Yes, yeah, you're late.
All right, there's the circuit analysis class. We're getting there. My next class doesn't start until 3.
Just so you know.
Oh, yeah, no problem.
What? That wasn't there before.
What? It's been sitting there for 4 days.
No,
I
it hasn't.
just told you that. You didn't believe me?
So I looked at the template. You didn't. You didn't even have the video that
It wasn't there yesterday. It wasn't there this morning.
Oh, I don't believe it. You guys.
Look at the date, November 12th.
Yeah, I can use that too.
It wasn't there.
No, it could have been yesterday at midnight, you know.
I didn't see it there this morning. I was on there this morning.
All right, so we'll do the first 2 first. All right.
You just add them,
All
right?
right, are we ready? Oh, where'd it go? All right, there we go. Everything's fine. Yeah. All right, well, we'll do the first guy first.
Just add
Find the total capacitance.
them.
C total is 5 microfarads. Capacitance in parallel adds. C total 1 over 1 over 1 microfarad plus 1 over 4 microfarad, which means it's some number smaller than 1 microfarad. And so 1 over, plus 4, 1 over, equals 1 over 800 nanofarads. 800
What's the difference between the
nanofarads.
first one and the second one?
This is in series, and that's in parallel.
Got you. I was just testing you.
You're just
See if
testing
paid
me?
attention.
Yep. All right. All right. Number 3, total capacitance. All right, so it's going to be, these guys are in parallel, so that's going to be a 5. And so 5 in series with 6, so total capacitance 1 over 6 microfarad plus 1 over 5 microfarad equals some number around a little bigger than 2.5 probably. No, I don't know.
1 over 5.
6, 1 over, plus 5, 1 over, equals 1 over 2.7. 2.7 microfarads. Okay, well, what time after the switches will I get there? Well, probably about 5 time constants, because that's almost fully charged. A time constant is RC, so the time constant is 1 millisecond. So the time after the switch closes will be 5 times that, implying 5 milliseconds. I'm done with that guy.
I didn't get it, but
All right.
seems right.
Now, it would seem to me that all things being equal, the inductors will be first on the test and the capacitor second instead of the order that I have them, if I remember to do it that way. Okay, L total equals 6 millihenry, because inductance in series adds. Inductance total equals 1 over 1 milli plus 1 over 2 milli plus 1 over 3 milli. So some number less than 1 milli. 1 plus a half plus a third equals 1 over. 450, we'll call it. 450? Yeah, 550. 550 microhenry.
You should put the formulas you would on a calculator.
1 plus a half plus a third equals 1 over key. Notice that you have to get the right, because this is milli, this is going to be a fractional thing, it's going to be in micro. All right. All right, now we got these two guys. Find the total whatevers. Okay, so I'd have to go 1 millihenry plus 1 over 2 millihenry plus 1 over 3 millihenry. So I go 2, 1 over key, plus 3, 1 over key, equals 1 over key, plus 1 equals. And then my answer has to be in millihenry, so if I don't put in any millihenries anywhere, I'm going to end up with millihenries when I get done. 2, 1 over key, plus 3, 1 over key, equals 1 over key, plus 1 equals 2.2 millihenry. 2.2 millihenry. At what time after the switch is moved will the inductor read about the so we still want 5 time constants. The time constant is still 1. The time constant is now different though. Anybody remember the time constants for an inductor?
What's one?
Is it R over L or L over R? Well, it can't be R over L because that'd be too large. So it has to be L over R. So if it's L over R, then I'm at 1 microsecond. So 5 time constants fully charged would be 5 microseconds. See, if it's the other way around, then it'd be 1,000,000 seconds, and it's not 1,000,000 seconds. All right, that solves that problem. Oh, goody. About time we get to something reasonable.
I think so.
All right. So, what happened to my problem? I think I know what's happening. I think I'm putting it over the other guy. Let's see how many I got. I got 1. I have 2. I have 2 of them. All right. Find the turn ratio. Okay, so turn ratio, turns secondary, turns primary is equal to voltage secondary, voltage primary is equal to current primary, current secondary. Do I know any of those things? Yes, I do. Okay, so turns primary to turns secondary
Make it
is
readable,
equal
please.
to the voltage of the primary, which is an RMS guy. 10 volts divided by 1 volt, that's going to be 10. All right. So now find the primary voltage. Okay, so 5 to 1, which is turns primary to turns secondary, has to equal voltage primary to voltage secondary, which is, I don't know, to 3. So voltage primary is 15 volts. Now, you may not count that as 3, right? You don't necessarily have to do that. So you could go 2.999 times 5 and say that it's something other than 15. You could, huh? Well, you could.
Do that again.
2.999
Times 5.
times 5, which would only be 14.995, right?
15.
So you could call it 14.995 volts, or you could call it 15 volts. Either way, it doesn't matter to me. All right. Find the secondary current. Okay, so turns primary to turns secondary is equal to current secondary to current primary. All right, so I've got 1 to 5 is equal to, I don't know because I'm trying to find it, to 0.616 amps. So current secondary, 0.616 amps divided by 5. 5 goes into there 1 time, 5 goes into 11 twice, 5 goes into 16 3 times. So I'd write down a final answer, 123 milliamps. I have 3 significant digits there, I have 3 significant digits here. Everything is fine in the world. Number 12. Find the primary power. Well, power primary is equal to power secondary. So why don't you just ask me for the secondary power? Okay, so power is I squared R, both of which we have, 0.37 amps squared times 1,000 ohms. 0.73 squared times 1,000, we'll call it 140 watts. 140 watts. That's the same either way. Okay, so that was 12. How many more do we have to do anyway? Should be done pretty soon, right? 13. Find the secondary power. Okay, well, power primary is power secondary. So I can go V squared over R. 75 squared over 40. 75 squared divided by 40, 140 watts. All right, well that was all right. 14. Where did 14 go? All right, that's 14. Okay, first of all, I have to have x of c, which is 1 over 2 pi f 1,000 times 1 microfarad. so 2 times pi times 1000 times 1 E6 minus 1 over K. 159 ohms. 159 ohms. X, oh, I did it. I'm done. That's all there is. Lots of other stuff there, but I just wanted X of C, so I'm done. Find the total impedance.
What is the answer for K?
159 ohms.
Did you get that one?
Yeah, I think so.
All right.
Stay with the program, homie.
There, 159 ohms. Now you could go angle minus 90 if you wanted to, but don't have to. All right, back to here. Find the total impedance. All right, so first of all, we need to find X of C. X of C, 1 over 2 pi 60 hertz times 1 microfarad. It's not going to be very much, is it? Oh, it might be. 2 times pi times 60 times 1 E6 minus equals 1 over 265 ohms. 265 ohms. Z equals square root of 500 squared plus 265 squared equals 270 ohms. How can that be? It could be. Oh, I didn't take the square root. I don't know what I did. 5,000. What did you get? 565 ohms. We'll call it 560. 560 ohms. Okay, we'll call it 570. I don't care. Round it up that way. Normally I don't round that way. If it's 5 and it's even, I keep even. Huh?
I'm confused there. The 265 came out as that, and then you. That was XC.
Well, you only have 265 is XC.
XC.
That's what 265 is. So I got to go and take the square of the resistance, square of the reactance, take the square root of it. Add it together, take the square root of it. Okay, 16. Finally, we get to some worthy problem. All right, so here we go. Well, number 16. Finally, we get to a worthy problem. We still need X of C. So X of C is 1 over 2 pi 60 hertz 1 microfarad. Didn't we just do that one?
Yeah.
265 ohms, right? All right. This is going to be angle minus 90 because we're going to have that. All right, now, impedance of the parallel path equals 1 over square root of 1 over 265 squared plus 1 over 250 squared. See, 265 squared 1 over plus 250 squared 1 over equals square root 1 over 182, and we need an angle. So we need the arctangent of 265 over 250 with a minus sign in front of it. 265 divided by 250 with a minus sign, arc tangent minus 47 degrees. Okay, now we need the impedance total is going to be 500 ohms plus 182 XY key, let's see, 182 XY key 47 with a minus sign equals second function changed to rectangular. 124 minus 133 I. 624 minus 133 I. We're going to do a rectangular to polar conversion. 265 XY key 133 equals third function. Oh, I didn't do that right. 624 XY key 133 with a minus 624 XY key 133 minus equals third function. Boom. Alright. So I've got 638 angle minus 12. This is degrees, that's ohms. Alright, so what am I looking for? Anybody know? Alright, so I want impedance total, so I've got it. So I'll go with 638 ohms, 638 ohms angle minus 12. The voltage across resistor 1, voltage across resistor 1 equals what? Equals what? We need total current. Current total. Current total equals voltage source divided by impedance total. 0.71. 0.71 volts divided by 638 ohms angle minus 12. 0.71 divided by 638. Boom. 1.1 milliamp angle 12. We don't want that one. We want to find the next guy. All right, so the voltage across the resistor 1 is 1.1 milliamps angle 12 times, what's resistance 1? 500 ohms. Oh, that's not bad. 5.5 volts? No. 0.55 volts. 0.55 volts. Angle 12. Okay, so the voltage across the parallel path, which is also the voltage across the capacitor, which is also the voltage across R1, R2, is going to be equal to what's the total? 0.71, right? 0.71 minus 0.55 and an angle of 12. Okay, so 0.71 minus. Okay, so I got 0.55 xy key 12 equals second function changed to rectangular 0.54 plus 0.1i. Okay, so it's going to be 0.71 minus 0.54, 0.17 minus 0.1 I. Voltage across the parallel path. 0.17 xy key, 0.1 with a minus sign equals third function changed to polar. We'll call it 0.2 volts at an angle of minus 30 degrees. Okay. 0.2 volts angle minus 30. 0.2 volts angle minus 30. And now we want the current through resistor 2. Okay, so the current through resistor 2. The voltage across resistor 2 divided by resistor 2. 0.2 volts angle minus 30 divided by 250. 0.2 divided by 250, 800 microamps, angle minus 30. Where are we? 800 microamps, angle minus 30. And I'll spot you the angles if you want me to. Okay. Do I have any more or am I done? I'm done? That's all there is? There ain't no more? There will be, of course, an extra credit question on the test.
In regards?
Well, it'll probably have to do with Raimundo's unit.